Okay, so welcome to the last lecture of this series. And today I'm really going to go into what many of the things that I told you about have to do with gravity. And so for that reason, I wanted to remind you of something that I mentioned last time, which is that actually quite generically, if you set up a gravitational energy density in a non-equilibrium state, and I will tell you in a minute or so how we can really associate this with a non-equilibrium initial state. Then, as a function of time, it will eventually form a horizon that often hides a singularity. And I argue to you that this is something like the initial process of thermalization. And I'd like to make that a bit more precise, but before doing so, I'd like to say a couple of words about the horizon and introduce some ideas from, let's say, modern ways of thinking about gravity and even quantum gravity. So the first thing I want to say is that GR, or if you do a semi-classical quantization of GR, so you take into account the leading quantum corrections, actually associates with an equilibrium horizon, an entropy, the famous Bekenstein-Hawking entropy, which is actually given by the formula A, the area of the horizon divided by 4 times the Newton constant in natural units. So A is the area of the horizon. Actually, let me write in particular equilibrium horizon. And it's typically the area of some compact S d minus 1, some transverse sphere to this curve here. So you think of this, for example, as being given by a compact sphere. Here I'm drawing an S1.
What S is? SBA?
S is the entropy named after Bekenstein-Hawking that I should associate with any black hole horizon. I don't have the time in these lectures to go into how you would derive it, but there are sort of heuristic arguments that started this game off. But you can use, for example, techniques of Euclidean field theory to argue, for example, that there exists like a second law of black holes, and the area of the horizon is precisely what plays the role of the entropy in the second law of thermodynamics. That's one good argument for it. But what I was going to say here, which gives a little bit more of the detail, so which comes together with a temperature, which is this famous Hawking temperature, T Hawking, which it depends on which black hole you're looking at, but let's take the classic case, the Schwarzschild black hole in flat space. It's just the inverse of the mass of this black hole. So the mass of the black hole defines the temperature, and the area of the black hole defines an entropy, and according to the laws of, let's say, semi-classical GR, those two, for example, satisfy all the properties of their thermodynamic equivalents, namely, for example, the laws of thermodynamics. So, e.g., the change of area is always non-decreasing in any physical process. Okay, so now I wanted to just say this because when we talk about now chaos and also potentially chaos among the eigenstates or the microstates, I want you to keep in mind that what we really have in mind is that we associate to this. So what I often call the black hole Hilbert space of dimension e to the entropy. So in other words, we think about there being an underlying number of microstates such that the entropy of the black hole is given by the log of omega, and this is like the number of microstates. And what I'm really talking about, if I talk about quantum chaos in the context of black holes, or even more widely of gravity, is that there is at least a sector of the Hilbert space of gravity which is associated with the entropy of the black hole, and those microstates satisfy strongly chaotic properties. Okay, so this is, if you want, omega is a number of microstates in a microcanonical window. At energy E of, let's say, the Hawking temperature. Okay, this depends again on which black hole you're looking at, but here, for example, it would be just the energy mc squared that corresponds to this formula T Hawking up there. Now, so that is a very general statement, but in many circumstances we don't really know how to do it. However, there is a set of circumstances where we can actually be rather concrete about this, and this is the arena of holographic duality that I want to rely upon in this last lecture. So this is the topic of holographic duality. Also often known as ADS-CFT duality, where ADS stands for anti-de Sitter space and CFT stands for conformal field theory. Now, what this does is it actually, let me just say that the idea actually comes from what we have here. So what we say is that the fact that S of the black hole is associated to the area of the region inside is what people refer to as this peculiar holographic principle, meaning that even though you have like a volume of space or space-time, the number of degrees of freedom, because you see we said that the number of degrees of freedom will be the log of the entropy, is actually extensive with the area and not extensive with the volume of that region. So it's as if everything was projected onto the boundary of that region. And this idea is basically encapsulated in the so-called holographic principle. So here I'm talking very heuristically. Here I will get more concrete. I just want to give you one more heuristic. So this is what people call the holographic principle. And what they essentially say is that if I take a region of space-time, or a space-time, which I'm here now sketching as, let's say, the inside of this ball, the sphere around it will be the boundary. This is just a sketch. As I said, we will make this much more concrete in this ADS context. Okay, then I'm supposed to say that everything gravitational that happens on the inside, or also sometimes known as the bulk, should be describable by degrees of freedom that live on the boundary, and also a theory that governs those degrees of freedom that live at the boundary. So for example, I may be interested in studying indeed such a thing in the presence of like a black hole here in the center. So now in the center of this region of space-time, somewhere inside, I have a black hole. And I can actually learn about the black hole by interrogating in hopefully an intelligent way these boundary degrees of freedom, or rather also the theory that governs the boundary degrees of freedom. So the classic way of doing it, for example, would be to essentially probe it by looking at what happens if I consider correlation functions of operators O in this boundary theory. So you're supposed to think of this cross here as being inserted on the sphere that surrounds this ball. And this will interact with the degrees of freedom that are inside. And for example, will be on the inside represented by some bulk operator that I call phi O that now lives inside. So there is like the radius of the sphere So here the radius is like at some fixed value that gives you where the boundary is. Typically that's r goes to infinity or r goes to 0 or something. And so once I go inside, I'm at finite values of this r, and of course it still depends on where on the boundary sphere I inserted it. And so by looking at all sorts of properties of correlation functions, and later on even more, let's say, sophisticated probes, I can use this field theory to interrogate what's going on the inside. And the principle here is encapsulated by saying that something like the generating functional of all correlation functions of operators of this field theory. So this is the boundary. Let me just call it already CFT because we're going to go into this ADS CFT context. So this generating functional of correlations of the CFT, when I insert arbitrary sources for any of the operators, can actually be calculated by instead calculating properties of this field phi using the techniques of, well, quantum gravity, or if I'm less adventurous, semi-classical gravity. So this is the idea, okay? But in practice, of course, it is rather difficult to define, especially this object independently. And so the whole game consists, in some sense, in trying to reconstruct what's going on here from what we know about this, because what we have here, this is the last thing I will say, this is like a normal quantum system. Such as a quantum field theory, or even some certain interesting quantum mechanical theories. So in normal, meaning that it doesn't actually contain explicitly gravity. Whereas this thing contains explicitly gravity, and so if I had full control over this, I would have already solved quantum gravity, which we haven't yet, and that would be too complicated for the time being. So if you want, for the condensed matter-oriented people among you, one way of saying it is that you take some normal, in inverted commas, quantum system, and you have gravity that arises from it as an emergent behavior. Now, one of the really important questions is actually, how do you go, let's say, from here to there? What are the properties of this CFT that encode quantities of interest in quantum gravity? And if you know that, if you know this boundary to bulk map, there's also an inverse bulk to boundary map, then you can say a lot of interesting things about quantum gravity by actually using more conventional techniques. And what I will argue now for the rest of today is that actually all of these chaotic signatures and all of these principles actually have a very important role to play in this procedure. Okay? So now this was very heuristic. I'm sure there are some questions. I'll open it for questions in a sec, but I will say that it's probably best to keep this maybe even for the discussion, because that would be the set of a whole semester of lectures, which obviously none of us have time for today. But are there any questions? I think there were some people that were stirring. Were there? Maybe the eyes in my back don't work so well. Okay, very good. So the point is that was some motivation. Okay, so in some sense, this holographic duality is supposed to be an encapsulation of this idea, really of this idea that the black hole Hilbert space scales, the degrees of freedom that it describes, scale with the area of the horizon, and we extrapolate it to a general principle of quantum gravity that any area of space-time should be describable by a holographic theory that lives on its boundary. But in actual fact, this doesn't work in any old situation. At least we don't know how to make it work in any old situation. The situation in which this is most well controlled is in the so-called anti-de Sitter context. So basically, best known realization of this is precisely this idea where I'm looking at asymptotically anti-de Sitter spaces. And that's basically the anti-de Sitter refers to the unique maximally symmetric solution to Einstein's equations that has negative cosmological constant. So we have now Einstein's equations with, so Einstein equations with a negative cosmological constant and with maximal symmetry. In any given space-time dimension, you get this space-time anti-de Sitter space, which for convenient reasons, one usually, if in general dimensions d, we look at it in dimensions d+1, and the reason simply being that the field theory now that we use to describe it will be in d dimensions because it's in one dimension less. Now, okay, so this will become clearer also as we proceed, but you know, I'm talking about like general states of this thing, and now I'm starting with one very special, very symmetric, very classical space-time. So the idea would be that, first of all, in a full quantum treatment of this very special, so any geometry will be something like a state, and this very pristine symmetric geometry will be the ground state, which seems kind of natural. This will be the ground state. And of course, I can add on top of it perturbations, which would be something like gravitational waves or other excitations. But I can also look at large deviations from the vacuum, and I would, for example, think of a black hole as being a large deviation from this. It would be a black hole in ADS. But moreover, the fact that I can solve Einstein's equations here is that what I'm really saying here is in some sense the classical limit of this. So I can also start by doing a semi-classical quantization, then I start with the classical representation of the vacuum, and this would be the ADS space. So what is this ADS space? Well, it's actually, as I said, it's it's a very symmetric thing. It's basically, you start with a strange space, which is something like Minkowski space, except that it has two time directions, R2, D. So you have like a metric which is minus, minus, and then has D pluses, has one time too many, D space, and two time. And this is something that you use now to embed anti-de Sitter space. So this is just a convenient way to embed anti-de Sitter space. So in RD, which is just an auxiliary thing, consider the following simple equation. Well, we just take the naturally invariant quadratic form under this metric. So we take minus x0 squared, so this is the first time-like direction, plus x1 squared plus xd squared, all the spatial directions, and then I also have this x minus xd plus 1 squared. And I consider an embedding which is given by a hyperboloid whose size is controlled by a parameter that I call L. So this controls also the size of ADS. So ADS d plus 1. You see, so I started in some flat space with a weird signature that had d plus 2 dimensions. I impose one quadratic equation, which again is also the natural bilinear with respect to this pseudo-Minkowski metric. And so I reduce the dimension of the space by 1. I get a d plus 1 dimensional geometry, which is now curved because it's a non-trivial equation, even though this is a flat space. That happens to be anti-de Sitter. And so I can use this embedding, for example, to find everything about the geometry. For example, I can find the induced metric by just inducing the flat metric onto this hyperboloid. I can find geodesic lengths by projecting geodesics in the ambient space, which are just flat, into ADS, and so on. I can learn a lot about this space from this embedding idea. So a visualization of this is often is basically, let's say, a two-dimensional ADS, where you take like, let's say, here, how did I label this? X1, X0, X0, and then here you have XD plus 1. I mean, where I'm literally looking at, so this will literally be, well, no, let's leave it like this. And then you have this hyperboloid, which is a hyperboloid of revolution, which basically has these transverse spheres. And I'm just drawing the a visualization of this. And basically, so this would be the ADS d plus 1 hyperboloid in R2, D. So, for example, here I have, like x1, I guess x0 and xd plus 1, they are negative, so that I can get rid of this sign. So they basically are the equation of a circle. So I think of this thing as that circular direction. Okay, and then I have one hyperbolic direction, which is the x1 squared here. And you can, of course, imagine how I can just, multiplex that like I do for example, high-dimensional spheres, except that here I have pseudospheres with the minus signs. So the message is this is actually an extremely simple geometry, but the simplicity, of course, is also due to the fact that it represents the simplest state in the theory. It represents the vacuum state. Now, a different way of representing this, and this is one more class of diagrams that I want to introduce, is that this space-time, if you analyze it now and you look at its asymptotic structure, you actually find that it has a time-like boundary. So that is something that's very different from flat space, Minkowski space, or asymptotically flat spaces, which have, like null infinity, but not in a really useful sense, any sort of time-like boundary on it. And so the way to see that aspect is that people often draw this same thing as a cylinder, where they say that Lorentzian time goes up from bottom to top. The mantle of this cylinder is, again, our boundary. So the boundary is actually, this time-like boundary is of the form R, the arrow of time, times the transverse sphere SD minus 1. So this thing here, that is an S1 in my picture, in the higher dimensional case becomes a D minus 1. And everything that's the mantle of the cylinder, this will be this boundary. And everything that's on the inside is the bulk. And so what I have here is I have the gravitational dynamics and degrees of freedom are in this interior. And most of the time, I will have my CFT on the boundary, which is the mantle of the cylinder. And for example, now this again is the vacuum state. So this is ADS d plus 1 is equal to, let's call it omega, the vacuum state. But you can compare this, for example, with the case when instead you have at the center a black hole, which will, of course, be one of the cases that we're most interested in considering. So I have still the mantle of my cylinder. And now on the inside, I have a region which is basically delimited by another spherical surface, another SD minus 1, which will be precisely the SD minus 1 of the horizon that I wrote here. And sometimes you shade it. On a blackboard, everything is in negative. So the black hole here is shaded white now. But so this will be what people also sometimes call an eternal black hole. Eternal because it is there forever. I'm only drawing like a finite region of time, but you're supposed to imagine, of course, that in principle it's the whole real line. And so this black hole has always been there and always will be there. And this would be so this would be like the ADS black hole, which is a particular kind of solution, which is a little less symmetric than this one. And I would think of this actually as the thermal state. So this would be like rho thermal, which is precisely the thermal state that I told you about maybe 1 or 2 lectures ago. And so now I can be, in this case, I can be very precise in the answer to the question that I was actually asked then. So in this context, it's very simple to say what this rho is and what this h is. So now this H is actually the Hamiltonian, literally, of the theory, the boundary theory. Okay, it's a Hamiltonian of the boundary. And the fact that I'm saying that here we're in the state that is given by the canonical density matrix with respect to the boundary Hamiltonian is to say that if I play this game now, so I ask what are the correlation functions of operators in this boundary, I'm actually calculating correlation functions of the kind trace of all of your boundary operators with respect to this density matrix. So I put insertions of my operators A of x1, A of x2, A of xn. Okay. So the thermal trace of any observable, local observable in the boundary field theory will be obtained by considering not the vacuum state, but the state that has in the bulk a black hole. And that's why, in a very precise sense, okay, the process of going from here to there, by instead of putting the equilibrium state in the far past, but instead putting like a highly excited non-equilibrium state by performing some sort of quench experiment, will be a precise version of what I wrote there on the board. And from this process, which I will now describe, we can learn about the thermalizing behavior of the boundary field theory, or if you want, from the thermalizing behavior of the boundary field theory, we can learn about properties of the black hole. And so I want to go through some of these exercises now, and I want to show you how I think in increasing time we go from more and more mundane to more and more interesting properties that will, in the end, really teach us something about the nature of at least in this case, ADS gravity. Okay, so that was quite a whirlwind introduction to this. I wanted to perhaps tell you about one more kind of probe that we can compute, which is not just an operator correlation function, but something that has to do with more global structures. But it's maybe a good time to pause for a question or two. Yes?
The signature of R2, D in the upper blackboard.
Yeah.
The d-dimensional space corresponds only to the purely positive part?
Yes.
Okay.
Yes, so you see you have d plus 2 directions here, and I have 2 with a minus sign, and I have then d with a plus sign. Yeah. But of course, I mean, in some sense, these are just coordinate labels. I mean, you can give them any names. I just happen to find it useful to have 0, you always think of time, and then, like what is extra time? Well, you could call it -1. Some people even call it -1, but I like to call it d plus 1. And then you have your spatial dimensions from 1 to d, like you usually do. Right. Okay, so the last thing I will introduce also in this sort of whirlwind way will be really a key realization in this business, which is a formula to calculate entanglement entropy. And this is known as the Ryu-Takayanagi prescription, or Ryu-Takayanagi formula. Or if you actually, in a non-equilibrium context, it is also sometimes called the Hubini-Rangamani-Takayanagi formula. So this was conjectured by now quite a few years ago by Ryu and Takayanagi, who in fact I think this year received the Dirac Medal of the ICTP for, well, in a large part this work. But at the time they really guessed it. It was a very inspired guess. But in the meantime, many proofs, well, not many, but a number of proofs of this formula have been provided. So this formula is correct to the level of a physicist's, let's say, rigor. What is funny is that trying to prove it is actually really very complicated, because typically when you prove something about entanglement entropy, you have to use some replica trick and so on and so forth. And the replica trick in the context of gravity is really, really complicated. So if one had first tried to derive it, I think one would probably have very quickly given up. So the fact that these two actually just provided a guess of what the outcome is very fortunate. Okay, so the point here is that consider rho for your theory, so a general density matrix. It could be this, it could be this, but it could also be some more interesting state, a pure state density matrix. So consider rho and also consider a subsystem which I call A, okay, of the boundary. So subsystem in this context, what I mean is, for example, a subregion. Oh, yeah, I should probably have written subregion. Okay. So if we take just a snapshot of this boundary cylinder and we flatten it out, people like to draw something like this. In fact, you can do sort of like taking limits in which literally you can think of the boundary as a flat sheet. But that's not necessary now. I'm just remarking on that. But so this is like where the field theory lives. And I said that we take some subregion, some geometric subregion A. Now, this may be some window onto this, I don't know, cut out some, actually, I should be, at least for some of the experts in the audience, I should be a little bit more, let's say, truthful. So here, that's the kind of thing, would be, for example, a Poincaré patch on the boundary, which is like cutting out some sort of diamond on the boundary. That diamond, if I flatten it out and put it like this, will be flat space, and this is the flat space that I'm thinking of. So this could literally be R1, D. Okay, this is now actual Minkowski space, the actual, R1, D minus 1. Dimension counting is important here. This is the Minkowski space that is dual to D plus 1 dimensional ADS. And so then the interior direction of this, if I go from the mantle to the inside, now let's imagine that it goes down like this. So I look into the bulk like this. Now, what I want to say is that I can define, of course, the reduced density matrix on A. This is trace over the Hilbert space on everything that's not in A, the complement of rho. And then the entanglement entropy S of the subregion A is just minus the trace of rho A log rho A. This is also known as the von Neumann entropy of the reduced density matrix rho A, but it is also often just called the entanglement entropy, and is of course a measure of the amount of entanglement between degrees of freedom on the inside and degrees of freedom on the outside. Now, what Ryu and Tageyanagi told us is that this can actually be calculated. The way that it's calculated is actually the following. You draw a minimal area surface, because now the space as I go in is curved because it's like this non-trivial state. It's like a ADS black hole, or it's ADS, or it's anything in between if I take some other density matrix. And so that means that there will be like an interesting shape that I can minimize. I can look at the minimal area surface that is anchored at the boundary between A and its complement. Okay, let's call this maybe sigma A. And then this surface, sigma, is the minimal area surface in the ADS D plus 1, which I say with a twiddle here if it's deformed, bulk. So you just write the energy functional of a minimal surface as you would literally for a soap bubble. You extremize it, and you find the extremum. And then Ryu and Takeyanagi said that just like Wittgenstein and Hawking took the area of the horizon, which, by the way, is an extremal surface in space-time, you take 1/4 g Newton, and you take the area of this sigma surface. And that is the entanglement entropy of the subregion A. And, well, there's a lot to say about this. But I will not really, of course, go into it. This is a whole subject in its own, in principle, because it relates somehow geometric properties to the properties of entanglement. But I wanted to introduce it because entanglement entropy is actually a great probe of thermalization. So at least one calculation I want to show you basically tracks the behavior of this entanglement entropy under such a process. Okay? Right, so let's do that actually. So I would like to tell you now, I would like to give you now a more concrete description of what happens if we start looking at the process of thermalization in a holographic quantum field theory. However, are there questions? Yeah.
Why do you say that entanglement entropy is a proof of thermalization?
Well, because, for example, if you have you might want to have a statement that you take, let's say, rho, the global density matrix, to be some pure state density matrix psi, where psi is some high energy non-equilibrium state, like some Cn n, as we did, for example, for ETH. So this is in some microcanonical window. And now if I look at the dynamics of this, I want to see that this system approaches, as time progresses, a thermal state. So one way of formulating this if I look, and I said already when I talked about ETH that the best way of thinking about it is that I look at some local observables, like some, I said, non-extensive observables that might be, for example, might be confined to a particular region. Then what you can say is you can compare the following. You can say, what about trace over everything that's not in the region that I'm interested in of the global thermal density matrix? Trace of HAC of rho, let me call it psi, okay? And I want to show that as time progresses, this actually converges to some canonical density matrix for the subsystem A plus perhaps some corrections of the type e to the minus s over 2. Because if that is the case, if I'm at sufficiently late time, so let's say t is greater than the thermalization time, now if I look at expectation values within the subsystem A, which will be evaluated by trace rho A of any operators that are inserted in A, they will be the same as the thermal expectation values of OA. Okay, I'm writing it now thermal, meaning rho A is equal to rho beta on A, okay, plus exponentially small corrections. And that's interesting because by just looking at what the density matrix does, okay, I understand, for example, what all the local correlations will do. And one way of convincing yourself that the density matrix actually behaves like this, or one signature of this, is if I find that the von Neumann entropy trace rho A log rho A minus, as a function of time, SA of t, okay, that this thing approaches for time greater than the thermalization time, let's say, the canonical entropy S beta on the region A, which is that the entanglement entropy approaches the thermal entropy approximately, again, up to corrections. Okay, so that was a little excursion again into statistical physics, but it's a good question. So therefore, the entanglement entropy of a subsystem is it's thought to be a very good probe because it is somehow, something that really takes into account all of the degrees of freedom of A and the entanglement of all of the degrees of freedom in A with its complement. Okay. And also, I guess for those who haven't actually encountered this before, it's actually also a beautiful thing to think about thermalization in this way, because what it tells us is that under unitary dynamics, in a pure quantum state, you can still understand the emergence of statistical physics in a local subsystem. So this is another nice way of thinking about quantum thermalization. It's of course tied in very closely to these ideas of ETH. Okay? Right. Very good. So in fact, this is one of the first things I want to show you. This is something that we have done a few years ago now, but essentially we studied the dynamics of the entanglement entropy in this way, and actually we found that it behaves like this. And only later did we realize, by of course also reading more statistical physics, that the actually underlying mechanism is ETH. And this is how we started thinking about ETH in the context of black holes. So let me sketch how we did this. Well, it's actually just a repeat of various figures that I drew, but I can associate to these figures, I can associate actual equations. So now we actually we go to our ADS cylinder, and let's say this is our initial time, and we set up literally a non-equilibrium initial state. Okay, this initial state we construct by a limiting process in which we basically insert a whole bunch of boundary operators, or sources for boundary operators that are localized at the boundary at time ti. And this state, you can write it down. This will be a CFT state. It will be literally the product of I is 1 up to n of some, they're called primary operators, that are on the circle here at ti. So I label them by their angles around the circle, and they're acting on the CFT vacuum. And this state, actually I will take a limit where there will be a continuous distribution, but this state can also be argued now with these operator insertions to correspond to a particular space-time metric. And this space-time metric is literally the metric where there is a shell of energy that converges. It's like you sort of fire an implosion here, literally. And this energy that is associated to this initial state shoots to the interior. And you can actually track this. We solved the equations. And indeed, at some point, a horizon emerges with also spherical cross-section. And this horizon here, well, hides a singularity. There is even a name for the solution. It's called the Vaidya ADS D+1 metric. But what was interesting for us is that we can actually, in the CFT, we can actually probe this. And for example, we can write down expectation values of any kind of operators, other primary operators, let me call them W1 up to WK in this state. And so if you want, what we can do is we can track things with respect to the pure state density matrix up to WK. Okay. And what we find, for example, let me not write down actually the metric. I could have written down the metric for you. But what we find, for example, is that we calculate the curve of, in particular, the entanglement entropy of some subregion A. So let's say at some given boundary time here, so this is T approximately, let's say, the thermalization time. We select some subregion, which in this picture will be some interval A. You know, this is just some interval along the circle, and then the rest will be A complement. And we look at the entropy of A, and what we find is that it has some early nonlinear rise, then it has a linear phase, and eventually it saturates at the thermal time, which is actually proportional to L here, the ADS length in this case. That is not particularly interesting, but this is the S thermal. So you have some linear rise proportional to T, And the fact that this rises ballistically is something that goes back to studies of Cardi and Calabrese and so on in CFTs. But here we have associated to exactly the collapse of a black hole. And what is interesting is that this linear rise of the entanglement entropy before saturation is something that's very universal, and you can actually argue that this linear in T phase comes from a very special surface. So this is work that came from Maldacena and Hartmann studying a BCFT quench. And basically, you can think of it as coming from a slice that hugs just the interior of the horizon. And this is like an extremal slice of the geometry. And so the probe that you compute, actually, the probe here it was blue, and now the probe that you compute is something like this. And at later times, it hugs more and more of this blue slice. And so basically, the linear rise is connected to some very universal property of the horizon of the black hole. But so I want to go on to later times because things are more recent in history of physics, but also more interesting compared to what we said in previous lectures. But what I wanted to show with this here is that indeed it is possible to make the idea that the formation of the horizon corresponds precisely to this thermalization time, dissipation time T beta can be made very precise and is correct. And if you actually analyze the kind of things that we did here, so we look at some pure state, which we can characterize really by operators acting on the vacuum in a very precise way, you can actually show that the reason that these things define a state that is approximately thermal is precisely ETH. Okay, so this is saying that this class of states here, and this was also studied in detail, this class of states basically are approximately thermal because of the eigenstate thermalization. Well, hypothesis, this is a little bit strange to say in this context. You can sort of show that these states satisfy the moments of these states look like the moments of the ETH ensemble. Okay, so the mechanism of thermalization that underlies the formation of a horizon, of a black hole horizon, is ETH. Okay, so I don't know, this maybe now sounds like not that exciting because probably most statistical physicists would have said that should be the case. But I think it is very nice that really there is some sort of quantum mechanical understanding of what actually the formation of the black hole horizon corresponds to, and it's ETH. I think this is very interesting and nice. So of course I say this here, right? But for lack of time, so I can't summarize all of the material. But obviously people have studied this very directly in the CFTs. And because CFTs are systems which often are under better analytical control than other less symmetric theories, you can actually say quite a lot. And you can go quite a long way in establishing ETH as the mechanism here analytically. Okay, so now the next thing that we wanted to say is there some way of understanding Lyapunov chaos? So you see, I'm kind of working through all of the tenets of chaotic dynamics now for the microstates that are associated to this black hole Hilbert space. So the next thing that I want to ask is whether there is some way that I can think of really chaotic dynamics. I mean, ETH is abstractly associated with these chaotic dynamics, but can we say something even more direct? And the answer is, of course, yes. So what we can do is we can ask about the scrambling dynamics of these black holes. And here also, we can answer this in the affirmative. So scrambling actually will correspond to something like shock wave scattering. Okay, and at the very end, after I've told you about this, I want to make some remarks now also about the spectral notions of chaos. That, in some sense, to me, well, I'll decide whether I talk about spectral notions of chaos or krill of complexity. Both kind of get at this spectral notion of chaos. But to me, that's sort of the most exciting because it really shows something about the actual microstates of the black hole, this black hole microstates, and it establishes them to be the microstates of a chaotic system that has things like level repulsion and so on. But basically what you want to do now is you want to use similar kind of ideas to study the OTOC for a black hole. Okay, so, well, want to study OTOC of the CFT dual to ADS, thermal ADS, or the ADS black hole. And actually, the way to do it is the following. So I'm going to be drawing like these diagrams now, again. Here I just made a remark, but now I need to explain a little bit more what it is. This is actually a Penrose diagram of the black hole. So let's draw it again. So what we have here is that we have one copy of the time-like boundary, a second copy of the time-like boundary, and this wiggly line is typically a representation of the singularity. And then what we have a property is that this is in some sense a quotient by the SD minus 1 of the black hole. So we take the black hole, and every point on this diagram is now an SD minus 1 in the space-time. Okay, so these SD minus 1, every point here really corresponds to a D minus 1 sphere. And then moreover, this diagram has a property that light rays always go at 45-degree angles, either this way or that way. And the particular light sheets that are traced out if I go from corner to corner is what I call the black hole horizon. So then you have the right exterior, you have the left exterior, and you have the interior, and you have the past interior of the black hole. And so here now, if I ask about correlation functions on the boundary, I have to insert them on one of these straight lines. So this will be every point here is a sphere, and the directions that make up the square here are basically radius and time in some combination, such that light rays that either fall into the black hole go on 45 degrees like this, or when they come out, they go on 45 degrees like that. And if I want a two-point function of two boundary insertions, I can put them here at some boundary time t boundary, and this two-point function basically is approximated by the length of the geodesic between these 2 points. You can calculate the two-point function also exactly, but you'll find that in the limit where there is a classical geometry that emerges, in the semi-classical limit, it's basically well approximated by the length of a geodesic. So this picture, where I'm anchoring something at left and right times, which I'm here both choosing to be the same, this is actually just the same as the correlation function of some operator L inserted here and some operator R inserted there with respect to the thermal density matrix, because I'm in the black hole background. And I'm writing this here because I just want to use this as a normalization. Because what I really want to do is I want to compare this I want to compare this with something where I take a second operator W and I insert it at some time t, WL, V of t, WR. And to compare with. So what I really want to calculate is this over that. Okay. And the way to see what happens here diagrammatically is actually the following, is that I start with, in principle, the same thing. So I have this guy.
Question?
1 second. Yes?
So this looks like universal for any operator, so this correlation function.
You have to speak a bit louder, sorry.
Yeah. I said that it looks like that it's independent of the operator we put there, because the length is the same universal. So it's for any operator it's the same result.
In some sense, yes. In some sense, it will be yes, because actually what will happen is that this OTOC will have this Lyapunov behavior, and you might say, well, there will be some dependence on the dimension of this operator.
I'm talking about the previous formula. This is the point function.
Ah, yeah, this is the W one, so that means that if I take this quotient, the behavior will actually depend on the properties of the V operator, but not the W operator, because it somehow cancels out in this normalization. So I'm just using this guy as a normalization. I'm not calculating it for you now because I don't need to.
You said it depends on geodesics, right? But
Yeah.
it's independent of W.
This thing here, no, there's a formula. No, there's a formula that involves the dimension of W and the geodesic length. But if I know the properties of the operator W, meaning its conformal representation, and the geodesic length, I can write down this two-point function. Yeah. So now what happens is that I still want to calculate this, but instead, actually, I insert at some previous time t, I insert this V operator. And what you learn from, for example, these are, now I forget the authors, I'm sorry. Veneziano, for example, right. Veneziano and 't Hooft also, well, how can you forget those names? But anyway, these guys studied essentially particle collisions in space-time, and this is precisely what we're doing here, because what happens is that this, you can think of like the trajectory of a particle. This will be the trajectory of a particle, and then there will be an outgoing trajectory and an outgoing trajectory. So it's literally like 2-to-2 scattering. The point is that because of this time separation t, if you make this time separation sufficiently large, and I will say in a second what sufficiently large means, then the center of mass energy when this collision happens will actually be a very large boosted version of the energy of the insertion here. So this will be a very high energy collision, essentially because of the geometry of the black hole. And the way that you calculate it, which is actually was done in the 80s by 't Hooft and later again by Veneziano, is that this is what people would call a gravitational shock wave collision. So by the time you go into the center of mass frame of this collision, it becomes a shock wave collision. But thanks to the work of 't Hooft, actually those things can be calculated relatively easily, because somehow again shock waves that hug what used to be the horizon of a black hole actually have very simple behavior. And again, you can write down the metric of all of these things explicitly. I have them in my notes. So the fact that you can write down the metric here explicitly is something rather nice. And it's much simpler than you might think. But what turns out to be the case is that this correlation function here can be calculated, and it's given at leading order as 1 minus e to the r. R is actually a function of the mass. I'll write it down in a second, of the black hole. E to the r times t divided by LADS squared. Okay? And then you go back to your dictionary that tells you, in this case, what is the temperature of the black hole is a function of the mass, which is accounted here in r. And what you find is that r over L squared is actually nothing but 2 pi divided by the inverse temperature of this black hole. So what this is saying is that the OTOC decays with 2 pi over beta times t, which is what we called the maximal Lyapunov exponent that was allowed for such a OTOC 4-point function. So this is saying that the Lyapunov exponent of the black hole is actually equal to 2 pi times the temperature. So the conclusion here, although again I'm going rather quick with this, but the conclusion here is that by calculating the OTOC in the field theory, we learn that not only are the states of this black hole Hilbert space chaotic, in fact, they are maximally chaotic. They saturate the bound on the black hole Hilbert space. Now, I think I'm pretty much out of time, which is a shame, because I have at least two other things I wanted to tell you. So what I think I will do is I will at least give you a sketch of how the complexity comes out in such a context, and then we can talk a bit more about the details or any aspects really that I talked about or you might want me to talk about in the tutorial section. Okay, so very good. So let me just conclude by saying something about, so why am I presenting things this way, by the way? I mean, remember also that we sort of go forward in time, and right now we have said, how do we understand thermalization around, let's say, the dissipation time. And now we also know something about T star, which you can actually also from this calculation associated with something that's logarithmic in the entropy of the black hole. So if that black hole is big, that is parametrically a large time. So we are now at this scrambling time. But we might want to know what actually happens as time progresses. And one way of probing it is, you see the entanglement entropy has already saturated. It won't tell us anything anymore. The OTOC will have saturated here, so it won't tell us anything anymore. So one of the questions is, what tells us about what goes on with this black hole at much later time? And the answer here is complexity. And of course, in the context of these lectures, I would say it's K complexity. And one way of arguing for this will be that now we go to the context. I must say that I look at a 2D black hole now. I have to be a bit apologetic about this, but I also have to be honest. We don't yet know how to do this in higher dimensions, but let's talk about it later. But in 2D, we can say this very precisely. And the point is that in the 2D black hole, I can just say now, I can go really in the fully quantum regime, and I can say that I can build a basis of this black hole Hilbert space. And this basis of the black hole Hilbert space is nothing other than the Krylov basis for the boundary quantum mechanics. And the reason is that the quantum theory of this boundary quantum mechanics here can be solved in terms of what people call chord diagrams. Chord diagrams are just diagrams that start and end at the boundary and that correspond to Wick contractions of Hamiltonians that are inserted in the boundary. And let me finish on that picture. I want to draw you one chord diagram and tell you how the Krylov basis comes out. So these are like Wick contractions. So you might have Hamiltonian insertions on the boundary. So this would be, for example, 4 Hamiltonian insertions. You can also have cases where these lines cross. There's no problem here. And then let's have maybe these cross. So these are all, this will be some moment calculation of the Hamiltonian, which you can use to calculate, for example, a partition function or any transition matrix element, whatever you want. And what you can point out is that you can actually do this calculation by using transfer matrix techniques that are extremely similar to the kind of thing that Tomasz has told us about, that correspond to a slicing. So red is now a slicing of this diagram, and every time I slice it, I get a state in the Hilbert space of the theory, and I can slice it in such a way that I go from a 0 chord state, which I actually can argue corresponds to the thermal state, to, let's say, a 2 chord state. Actually, sorry, this one is not allowed. I go to a 1 chord state. I can go to a 3 chord state. I can go to a 1, 2, 3, 4, 5, 6 chord state. And I can go to a 1, 2, 3 chord state. Okay. there are some rules which I'm following. So what I'm having, I have an evolution where I go from a state in the Hilbert space which has 0 of these chords to one that has 3, 6, 3, 1, 0. This will be a contribution, for example, to calculating the thermal partition function. But I can actually describe it by calculating the transfer matrix that takes me from one slice to the other. There is a T transfer matrix. And guess what? The basis of these chord states, the basis of n is equal to any of these states, n is equal to something. This is precisely the Krylov element, nth Krylov element for the boundary Hamiltonian. And the transfer matrix T is tri-diagonal in the chord basis, which identifies the chord basis, the basis of the Hilbert space, as being the Krylov basis for the boundary. And now these things, if you take a classical limit, become literally the lengths between the two edges, between the two sides of this boundary, so something like this. And the length is given here in the quantum sense by the n of the Krylov basis. Okay, I can take a limit where this becomes a continuous variable, which is the classical limit. It becomes the length of the boundary. And what have I said now? I've said that the length of the boundary is associated to the n of the Krylov. And so that means that the time evolution of n, how big is n? The expectation value of length actually goes to the expectation value of n in the boundary quantum mechanics. And so therefore length is actually given as Krylov complexity. And this is something that we can track in practice from very early times to very late times, and that still has non-trivial evolution at these very late times here. So K complexity basically will be not only a very interesting probe of thermalization, but now we've gone, and I'll conclude on this remark, we've gone from sort of like looking at signatures of chaos and reproducing things to actually saying, look, you can use chaos and complexity to actually construct the evolution of space-time as a function of time at extremely late times. Okay? So I'll conclude here, and I'm sorry that I had to go a bit more quickly today, but that's always how it goes with four lecture courses. So thanks for your attention, and there'll be still the tutorial.
Questions? Taking some inspiration from this black hole calculation, is it possible for you to predict what kind of properties should a many-body system have so that it is maximally chaotic? Because even with the SYK type model, we have this saturation of Lyapunov exponent only at small temperatures, but not at larger temperatures. So is it possible to back construct some many-body model?
So you're asking, well, I mean, one possible answer would be that, but I'm not fully convinced of this, I should say, but that this might be the same question as the question of when does a many-body system have a good bulk dual. And there have been criteria that have been conjectured, to some extent tested, but it's not known what is the full set of criteria. But this would, for example, be that you have something like an emergent conformal symmetry, which is the case in the low energy limit that you're talking about. That you have something like a large gap of excitations between the vacuum and the higher states. The problem is that already in SYK that is weakly violated. That you have a good continuous large n limit, and you might also put in something like these bounds on transport coefficients such as viscosity over entropy density. But you know, they're sort of like supposed to be a set of criteria that tell you that you have a good bulk dual. They hopefully are the same as the criteria that you're asking for, but it's not known, so I don't want to make a definite statement. Yeah.
questions to Julian.
Yeah.
On